So let me get started with announcements for today. The first homework assignment, the Getting Started with WebAssign assignment, is due today, tonight, at the 21st. So it's due tonight. That should be fairly straightforward. You're really just following the simple instructions on how WebAssign works. The first homework assignment on chapter 1, which is the longer of the two for chapter 1, is due on Monday, the 26th. The second homework assignment for chapter 1 is due on Wednesday, the 28th. And I've moved our first quiz back from Monday to Wednesday next week to give you guys a week to prepare for the quiz. The first quiz will be on Wednesday, the 28th. My general policy for quizzes and tests is you get one sheet of notes that you can use as a reference sheet for equations and things you have trouble remembering. So if you have trouble remembering all the metric prefixes, you can put a list of all the metric prefixes on there. You can put whatever you want on it. You get one sheet of notes. It should be handwritten, and just, the size of one regular sheet of paper. And lastly, the significant figures worksheet is due on Wednesday, the 28th. Names? What? Mello? Okay, and Joseph. So, the significant figures worksheet, that I have a few extra copies left. So I seem to be running low, and a bunch of you already turned it in, which is great, is due on next week, Wednesday. Any questions? The quiz will be in class. We'll have lecture for the first part of class and then quiz for the second part, so that if you finish the quiz early, you can just head out early. Okay, I'm going to continue on with chapter 1. So we were discussing scientific notation. Let me just double check that I'm in the, yeah, okay. So we talked about scientific notation. In scientific notation, a number is expressed as the product of two numbers. Some number between 1 and 10, which the fancy name for that is mantissa. It's also, there's another name for it as well that I can never remember because I thought mantissa sounded cooler. But it doesn't need a special name. It's just some number, the number part, and a power of 10. So to convert a given number to scientific notation, you first move the decimal point to the position after the first non-zero digit. That's how you get a number between 1 and 10. So a number in scientific notation will always have one non-zero digit followed by a decimal point followed by more numbers. So like 2.5 times 10 to the 7. So you move that decimal point to the position after the first non-zero digit. Every step you move the decimal point to the left, you have to add 1 to the power. Every step you have to move the decimal point to the right, you subtract 1 from the power. So here, 950,000, you need to move the decimal point 5 places to the left. So that will be 9.5 times 10 to the 5th. So that was a quick review of scientific notation. The metric system uses the acronym MKS system from the standard units of length, mass, and time, which are the meter, kilogram, and second. The reason we call it the MKS system is to differentiate it from another version of the metric system that uses standard units of centimeter, gram, and second, which was built on a slightly different way of thinking about units. That used to be a lot more popular, but isn't so popular anymore. It's a base 10 system, which is a lot more convenient than the British system, which uses several different bases because it's a confusing mess of various old systems glued together. And it's administered by the International Bureau of Weights and Measures, the Bureau International des Poids et Mesures in Paris, and it's the International System of Units, which is abbreviated as SI, because adjectives go in a different order in French, because it's System International in French. And it contains 7 base units. The 7 base units are the meter for length, the kilogram for mass, the second for time. Those are the 3 most commonly used units. Then we have the ampere for electrical current. You've probably seen that on various electrical devices. You know, your phone charger is so many amps. Kelvin for temperature. So Kelvin temperature is like Celsius temperature, but instead of starting at the freezing point of water, like Celsius does, it starts at the coldest temperature there is, absolute 0. The mole, which is a way to count, it's a number, but it's a way you use in chemistry to count how much of a molecule or how many of a molecule or an atom you have by weight. So it's a way to count atoms and molecules. And then there's the candela, which is a measure of luminous intensity. The common prefixes of the metric system. There are prefixes for larger numbers and prefixes for smaller numbers. They all correspond to powers of 10. So if you want 1/10 of your base unit, that is deci, which is abbreviated with a lowercase d. 100th is centi, which is abbreviated with a lowercase c. Your name? Sure. That's not due right now, but you can turn it in if you want. If you want 1,000, that's milli, which is abbreviated with a lowercase m. That's the one that's easy to get confused because there's also one abbreviated with an uppercase m. And there is a problem on your homework where you can make that mistake. If you want a millionth, so after 1,000, they start going by factors of 1,000. So a millionth, 10 to the minus 6, that is micro, which is abbreviated with a lowercase mu, which is the Greek letter mu, but it looks like a U with a line on the front. It's commonly typed with the letter U. Nano is a billionth, 10 to the minus 9. That's a lowercase n. Pico is a trillionth. That's a lowercase p, and it's 10 to the minus 12. For bigger units, there is a 10 and 100, but we're not going to use them, so I'm just going to skip them. They're like deca and hecta. Yes. All these slides are on Blackboard. And these are also in your book. There's a table in your book. But yes, all the slides are on Blackboard in the lecture section in the folder slides. And I also attached the slides that I used for each day to the recordings from previous lectures. So for larger ones, 1,000 is kilo, 10 to the 3rd. A million is mega. That kilo is a lowercase k, like kilogram. Mega is a capital M, and that's 10 to the 6. Notice that mega is a capital M, milli is a lowercase m. Giga is a billion. That's 10 to the 9. That is a capital G. And then the next one up that's not on here is tera, which is a trillion. That's 10 to the 12. That's a capital T. And they do continue, but you're only going to encounter those in computing. The next one up is penta. Significant figures are a method of expressing measured numbers properly, expressing the precision of your measurement accurately. So any mathematical operation like multiplication, division, addition, subtraction cannot give you more significant figures than you started with. For example, 6.8 has 2 significant figures. 1.67 has 3 significant figures. if I need to multiply 6.8 by 1.67, my answer needs to be rounded to two significant figures because I can't end up with a more precise measurement than I started with by multiplying two numbers together. So 6.8 times 1.67, and your calculator, you're going to get 11.356, and you will round that to 11. This is particularly important when you divide, because when you divide, you tend to get lots of extra digits. And your calculator knows nothing about significant figures and will do nothing with significant figures. It will just give you as many digits as it can. It will vomit them up. So when we use a hand calculator, you can end up with results like 6.8 times divided by 1.67 is 4.0718563, which you would then round to 4.1. Not all of those numbers are significant. So the general rule is you report only as many significant figures in the result as in the quantity with the least. That is the general rule you can always use in this class. Strictly speaking, the rule for addition and subtraction is slightly different than the rule for multiplication and division. So for multiplication and division, 6.8 centimeters divided by 1.67 centimeters, the units cancel, you're left with 4.1. When you round off 4.0718563, the limiting term is 6.8 with two significant figures. For addition and subtraction, strictly speaking, you should use the number of decimal places. Most of the time, doesn't matter. I will not mark you off for any problem if you do just use significant figures in this class, because your book just talks about significant figures. My general policy on that is that I will treat either one as correct. If you use the number of decimal places, I'll mark that correct. If you use the number of significant figures, I'll mark that correct. So there'll be two right answers. So here, for example, and a lot of the time, they'll give you the same answer. So here we have 5.687 plus 11.11 gives you 16.80. The limiting term is 11.11 with four significant figures, or it's the limiting term is 11.11 with two decimal places. Both of those methods give you 16.80. They'll give you the same number of significant figures. Usually, the number of significant figures doesn't change. There'll be a couple places where I will explicitly tell you to use more significant figures than you would get by using the significant figure rule. That's usually when we're taking a bunch of measurements and averaging them. That allows you to get more significant figures because of this adding rule. But I'll be explicit about that. There's a lab where we're going to do that. And I'll just tell you that you should use this many significant figures on that particular spot. So the rules for counting how many significant figures a number has. All non-zero digits are significant. So 223.4 and 234 both have three significant figures. Any zeros in between non-zero numbers are significant. The only things you might drop are zeros on the front or zeros on the end. So captive zeros in the middle always count. So 20.05 has four significant figures. 407 has three significant figures. Any leading zeros on the front, never count. Because in theory, you can put as many zeros on the front as you want. They just never count. Because, if I just add some extra zeros on the front here, it doesn't change the number. All those serve as a purpose is to locate where the decimal point is. So here, 0.000035 only has two significant figures. Trailing zeros on the right, on the end, need to be determined from context. But the usual rule of thumb is if there is a decimal point, they count. If there isn't one, they don't. So 45.0 has three significant figures, but 4,500 probably only has two significant figures. They're always significant if there is a decimal point. On tests, if I wanted to do 4,500 with four significant figures, like shown here, I would just stick a decimal point at the end. to make there be a decimal point so that all the figures are significant. Because on tests, I often want to use tests or quizzes, I often want to use nice round numbers. So the math comes out relatively nice. But I want you to have a certain number of significant figures. So I'll do that. Now, exact numbers, like numbers of people, items, etc. If I have 8 cupcakes, that's an exact count. Or, I have 3 laser pointers here. That is exactly 3. Those are assumed to have an unlimited number of significant figures. There's no error in that count. So we can just ignore them. And in general, when we determine the allowed number of significant figures, we generally have to round off numbers. If the first digit to be dropped is less than 5, we leave the preceding digit unchanged. So rounding off 3 significant figures, 26 point. If we have 26142 and we want to round this to 3 significant figures, we start counting from the first non-zero digit, 1, 2, 3. Then we look at the next digit. That is a 4. Because it is a 4, that means the number is closer to 26.1 than to 26.2. So we round it to 26.1. So if the first digit is 0 to 4, first digit to be dropped is 0 to 4. That means it's closer to the preceding value. So we leave the preceding digit unchanged. We just drop it, those numbers. But if it's 5 or greater, it will be closer to the next value. So you have to round up. So 10.063, the first digit to be dropped is a 6. So we'll have to round that up to 10.1. Because 10.063 is closer to 10.1 than it is to 10.0. Now, the one weird case you can have is if you have something like this. 0.997. So if you have 0.0997 and you want to round this to 2 significant figures, well, the normal way you do this is you go, okay, first non-zero digit, second non-zero digit. Let's look at the next digit. That's a 7. That's going to be closer to the next value up. I will round up. 9 of 1 is 10, so 0, carry the 1, 0, carry the 1, 1. But this has 3 significant figures. Because I had a string of nines where everything got carried up, carried up, I can end up with an extra significant figure. All I need to do is just drop the last 0. So 0.997 rounds to 0.10, to 2 significant figures. That will only happen when you have a string of 9s. It can only happen when you have a string of 9s. So it very rarely happens. Here's a more straightforward one. 5.0 times 356 gives you 1780. Our limiting number is 5.0 with 2 significant figures. So if we round off 1780 to 2 significant figures, that rounds to 1800. Any questions? Okay. So in general, when you make a measurement, the number of digits you use is depends on the precision of the measurement. The general rule is that you have the general rule, like if you're measuring with a ruler or something like that, you could estimate 1 extra digit. So for example, if we read the arrow on the length of the 1 estimated digit is required and more are not allowed. So here, if we read the length represented by this arrow, that is 54, and then we have to estimate a point in the middle, that's 0.5. 54.5. So it would be incorrect to say it was at 54. It would also be incorrect to say it was at 54.66667. You need one estimated digit. More are not allowed. That's the general rule of thumb. I'm not going to be super picky about that in this class. I'll just tell you how many digits I want. Because we have a few different ways of measuring things, and that can vary. Like, if you're using a digital scale, you just use the digits on the scale. But when you're measuring with a ruler, in general, you can estimate. But I believe in a lot of cases, I'll just ask you to do things to say millimeter precision. This measurement has three significant figures. It's 54.5. So in numbers with so the rules for significant figures, in numbers with a decimal point, leading zeros are never significant. Trailing zeros are always significant, and zeros between non-zero numbers are always significant. In numbers without a decimal point, trailing zeros are never significant. And in all numbers, zeros which appear between non-zero digits are always significant. So 3,400 here has two significant figures. The trailing zeros are not significant. There's no decimal point, so those are not significant, the trailing zeros. And this has two significant figures. Here, the leading zeros are never significant, but the trailing zero is significant because there is a decimal point. So this also has two significant figures. Here you have leading zeros, they're not significant. A zero in the middle, that will always be significant. So the leading zeros are not significant. The zero in between other numbers is significant, and the regular numbers are, the non-zero number digits are significant. So this has three significant figures. Here we have 2050. There's no decimal point. So first we have a zero between other numbers. That is significant. But we have a trailing zero with no decimal point. That is not significant. So that last zero is not significant. This has three significant figures. To remember the sort of zeros in the middle thing, your significant figures will always be one block. So you'll never have any non-significant figures in the middle of the number. And here we have a number in scientific notation. One of the nice things about scientific notation is that all the digits in this mantissa are always significant. So this 6.02 times 10 to the 23rd, which is the number of particles in a mole, has three significant figures. If you write it out, you write it out like this, with far too many zeros, but none of those trailing zeros would be significant. The general rule, these are all significant figures in scientific notation. So if you want to be clear about the number of significant figures in a number, you can always write it in scientific notation, and then all the figures you write will be significant. So here we're rewriting these numbers in scientific notation with the proper number of significant figures. So 0.0257. Well, first we have to move the decimal point 2 places to the right, which gets us 2.57 times 10 to the 2. And this has three significant figures. The leading zeros do not count. Then we have 125.6. Here we have to move 2 places to the left. There is all of these digits are significant. So we get 1.256 times 10 to the 2 with 4 significant figures. Here we have 93 million. We have to move the decimal point 7 places to the left. So we're going to get 9.3 times 10 to the 7. The only figures that are significant are the first two. There's no decimal point. So those trailing zeros are not significant. So 9.3 times 10 to the 7. Here we have negative 65,800.0. While this is a negative number, you just keep the minus sign when you convert it into scientific notation, we have to move the decimal place 4 places to the left, but there is a decimal point. So we have to keep all of these digits because they are all significant. So this is negative 6.58000 times 10 to the 4. So because the decimal point is here, these 3 digits are significant figures, so we have to keep them. And then lastly, we have 0.0000278. This we have to move the decimal point with 6 places to the right. So this will be 2.78 times 10 to the minus 6. The leading zeros are never significant. Here, we're going the other way. Things written in scientific notation, all the digits are significant, so you have to preserve them all. So 2.57 times 10 to the 2. Well, to go backwards, well, this was 10 to the 2, so we'll have to subtract 2 from this to get rid of the 10 to the 2, which involves moving 2 places to the right. So that will be 257. 2 places to the right. Here we have 1.25 times 10 to the minus 7. So here to undo the 10 to the minus 7, which will be 7 places to the right, we have to add 7, which is 7 places to the left. So we'll move the decimal point 7 places to the left, and we'll get 0.000000125. There are 6 zeros between the decimal point and the 1. Here we have 9.3 times 10 to the minus 4. Again, we'll have to move to the left 4 places, in this case, 4 places to get rid of the minus 4. So we will get 0.00093. 3 places between the decimal point and the 9. Here is an interesting one. We have 6.5800000. Well, all of these numbers are significant, so we have to keep them all. We're going to move the decimal place 4 places to the right to get rid of the 10 to the 4, but that leaves us 2 zeros after the decimal point. So this will be 65,800.00 because we have to keep these digits. And then lastly, we have 2.78 times 10 to the minus 1. We are going to move the decimal point 1 place to the left. So that's 0.278. So let's go through this list and put the numbers in order of decreasing number of significant figures. Most significant figures to least significant figures. So which of these has the most significant figures? Anyone? Yes. You're saying this one? Anyone else? Any guesses? Yes. So this one. That one. Okay, so we have a shot at this one, and this one. Well, the correct answer is this one with 1, 2, 3, 4, 5, 6, 7, 8 significant figures. The 890,000 one has 1, 2, 3, 4, 5, 6, 7 significant figures. And the 6,001 has 1, 2, 3, 4, 5 significant figures. So yes, that is the most at 8 significant figures. Though the 890,000 was a good guess, it's next at 7 significant figures. What do you think is next after that? It is that first guess of 60,001, which is 5 significant figures. Any guesses on what is next? You say bottom. Anyone else? What? This one? So the one on the bottom is 3. This one is 4. So the 1,501,000 is 4 significant figures, and 4,520 is 3 significant figures. In both cases, the trailing zeros don't count. And then lastly, 0.00030 is two significant. So again, quick review of the rules. In numbers with a decimal point, leading zeros are never significant, trailing zeros are always significant, and zeros between non-zero numbers are always significant. In numbers without a decimal point, the only change is trailing zeros are not significant, and in all numbers, zeros which appear between non-zero digits are always significant. And the significant figure worksheet has a nice summary of those if you're working on it still. And if you want a copy of it, there are copies of it up on Blackboard if you want to look at it later. So for example, 3,400,100 here has no decimal point. So the trailing zeros are not significant, and this has 5 significant figures. So these are the rules for significant figures in calculations. These are the strict proper rules. For addition and subtraction, the calculated answer should only contain the fewest number of places after the decimal point of any number used in the calculation. And for multiplication and division, the calculated answer should contain only the fewest number of significant figures of any number used in the calculation. General rule of thumb, you're always safe sticking with the significant figures. Also, it's good practice to wait until the very end to round. There are a few cases where the addition and subtraction thing could mess with that, but it is good practice to wait until the very end to round, because that keeps you from, you can build up rounding errors, which could lead to some funny answers in calculations. But yeah, so for example, 1.455 plus 3.2, you would round to 4.7 because one decimal place, 2 significant figures in the answer. But if you use significant figures, well, this limiting term also only has 2 significant figures. So you get the same answer. But here's a case where you would get a different answer, 1.40 plus 0.21. This you would keep the 2 decimal places, and you'd have 3 significant figures in the answer. So strictly speaking, you can end up with going slightly up in significant figures. But this is sort of a rare occurrence. Yes, this can happen. So if you did significant figures, you'd round it to 1.6. And on a quiz or an exam, I would not be picky about that. I would accept both answers. And then for multiplication and division, you always do the significant figures. 1.40 times 0.21 is 0.294, which you're going to round to 2 significant figures in the answer, which is 0.29. And the more complicated one, 6.023 times 1,000 divided by 1.56 times 10 to the 5 gives 0.038589743 on your calculator. But you only have one significant figure in the 1,000 here. So you'll round that to 0.04. And here we have 6.023 minus 1,001 divided by 23.002. I mean, not 1,001, 1.001. Here you would do addition by fewest number of decimal places and then division by significant figures, but you could actually just use significant figures as a limiting factor. You have 3 decimal places in the numerator in both cases. You end up with 4 significant figures. And then when you divide, your answer should have 4 significant figures. So you'd round this to 0.2183. So in general, in mixed calculations, you do the addition and subtraction first, determine the number of significant figures, and then complete the problem rounding up. But also, I'll always accept just using the number of significant figures in the input as your limiter, because I'm not being super picky in this class. So let's talk about a general approach to problem solving. General rules. You start, first and most important step, read the problem. Then what you want to do is you want to identify what they're talking about, identify what principle applies to it. And it's very useful to write down what you know. Write down the given quantities with their units, maybe make a sketch of what's going on so you have some idea of what you're looking for. Then determine what you're being asked to find. Write that down. Once you have a list of the things you know and what you're looking for, that makes finding the appropriate equations a little bit later a lot easier. Then the next step would be to check your units, make sure everything is in the right units for your equations. If there are any conversions you need to do the appropriate conversions, because a lot of the time for, check what units you're being asked for in the answer, if you're being asked for that, or check that your equation is expecting certain types of units. So a lot of the common equations are expecting standard units. So, if you're going to use the equation for acceleration, it's expecting velocity in meters per second. If your velocity is in kilometers per hour, you have to correct for that. So make conversions if necessary. Then survey your equations, find the appropriate one. If you know what you're looking for and what you know, well, in all likelihood, your equation will contain what you're looking for and what you know and not anything else. So that'll let you figure out what equation you need. You might have some extra numbers, but that's sort of the idea. And then do the math using appropriate units, round off and adjust the number of significant figures. And that will be your answer. So here's an example. Here we have the Earth goes around the sun in a nearly circular orbit with a radius of 93 million miles. So how many miles does the Earth travel in making one revolution around the sun? So let's identify what we're talking about. Well, we're talking about stuff moving in a circle. So we're going to be dealing with circles. So we have the Earth going around the sun in a circle. I can draw a picture. We know the radius. Our radius is equal to 93 million miles. So 93 times 10 to the 6th miles, or I'll write it in proper scientific notation, 9.3 times 10 to the 7 miles. And we want to know how far the Earth travels in one revolution around the sun. So one complete rotation. Well, that's a question about circles. So, important thing, we're dealing with circles. We have a radius that is given, and we are looking for the circumference. Because how many miles the Earth travels making one revolution, that is the circumference of the circle. So we determine what parts of the question are important, that's the underlying parts, and how to attack the problem. So this is a question about circles. It's asking for the circumference of a circle with a given radius. So we have a circle with a radius, we're looking for the circumference. So we need an equation for the circumference of a circle. Well, the equation for the circumference of a circle is 2 pi times the radius. Our radius is 93 million miles. Our answer also needs to be in miles. We don't need to do any conversions. We're good. Our equation, circumference equals 2 pi times radius. Pi is a constant, it's 3.14159. So if we do the math, 2 times 3.14159 times 93 million miles That's 2 times 3.14159 times 9.3 times 10 to the 7 miles. Well, 2 times 3.14159 times 9.3, that is 58.433574 times 10 to the 7 miles. Our input, 93 million miles, had 2 significant figures. The 2 is just a number in the equation. It's an exact value. We don't need to worry about it. Numbers and equations, you never need to worry about. They're significant figures. And we had more significant figures for pi. So we round to 2 significant figures. That would be 58 times 10 to the 7 miles, which is 5.8 times 10 to the 8th mile. So 5.8 times 10 to the 8 miles, or 580 million miles, is the distance the Earth travels in one revolution around the sun. That's sort of the approach you can take. And this is the end of chapter 1. The equation at the end of the chapter, which the student needs to be familiar, is the density equation. The density is mass over volume. We'll be doing a lab about density in our second lab. And volume is mass over density, but there will be a problem on the quiz about this, which will be before our second lab. So remember that this equation for density. It uses rho, but if it makes it easier to remember, you can also write it as capital V density is mass over volume. So that's the end of chapter 1. Any questions? So we still have a decent chunk of time. So I'm going to get started on chapter 2 to make sure we'll have enough time for the quiz when we get to it. I'd just like to be a little bit ahead of schedule because I had to shuffle some things with the schedule recently. So, stop share. We should, because that stupid bug that I don't know any other way to fix. So chapter 2 is about motion. We're going to talk about how to describe motion, and how motion works. And then in chapter 3, we'll add the concept of force. This is chapter 2 on motion. So physics is the most fundamental physical science. Everything builds off of physics. It's concerned with the basic principles that describe how the universe works. So it deals with things like matter, motion, force, energy. You know, the basic building blocks that everything else is built off of. That's part of what attracted me to physics. I am a physicist. So some of the areas of study are things like classical mechanics, which most of what we're going to cover sort of falls into. So the chapters 2, 3, and 4 fall under classical mechanics. Waves and sound, we'll talk about that in chapters 6 and 7. Thermodynamics, which is the study of heat. That'll be chapter 5. Electromagnetism. Technically, we'll do a bit of that in chapter 6 and 7 as well, because we'll talk about electromagnetic waves. We're not going to go into much detail there. What we will not be talking about is quantum mechanics, which is the study of the very small and how they are weird. Atomic, we may, if we have time, we may cover a little of atomic and nuclear physics, which is, the study of atoms and nuclei and things like that. And I may mention some stuff about relativity. I'm not going to talk much about relativity. That's the study of large-scale gravity, the really big. When gravity is strong or when you're moving very, very fast, that's when relativity is different. And these are sort of the two most basic fields. you could actually sort of split all of physics into stuff built off quantum mechanics and stuff built off relativity. And one of the big problems in physics today is that those two fields do not mesh. Like, we know they should work together. We know there should be, if we're going to describe everything, our understanding of the universe should be able to mesh gravity, our understanding of gravity and relativity with our understanding of quantum mechanics for everything else. And they do not. The math is not compatible. So we need a better theory, but the problem is the other theory has particularly broken to help us find the better theory, which is one of the sort of problems we have. But we're getting there. But in this chapter, we're going to be discussing motion. Motion's everywhere. Walking, driving, flying, etc. We all move around and do things. So this chapter will focus on the definition and discussion of motion. We're going to be describing motion using the concepts of speed, velocity, and acceleration. There's two basic kinds of motion, and all motion can sort of be thought of as a combination of these two basic kinds. These are straight line and circular. We'll start with straight line motion, then later we'll talk about circular motion. When we define motion, well, we need to be able to talk about an object moving. Well, if an object is moving, where it is changing. So the first thing we need to be able to describe is where the heck the object is. So position is the location of an object. And to describe the location or position of an object, we need some sort of reference point. This is an origin or a zero. So if I was going to talk about position in this classroom, a reasonable origin might be that corner down there. And then I could say how high up something is, how far away from this wall something is, and how far away from that wall something is. That would be a reference point. And if an object is in motion, it's undergoing a continuous change in position. Its position is changing over time. And to describe that motion, well, if it's changing over time, we want to talk about how it's changing over time, how fast it's changing over time, what rate is it changing over time. So to describe that motion, we need a combination of both length, to describe where it is, and time, to describe how it's changing over time. So we use a combination of length and time to describe motion. And that leads us to the concepts of speed and velocity. And there's sort of a subtle difference between speed and velocity. So in physics or in physical science, speed and velocity are two different things, similar but different things with different and distinct meanings. Speed is how fast you're going. It's a scalar quantity. It only has a size. It doesn't matter what direction you're going, it's just how fast you're going. While velocity is a vector. It has a size and a direction. So velocity, so the speed of a car, you have a car going at 80 kilometers per hour. The velocity of a car is a car going at 80 kilometers per hour north, or in the X direction, or up. You have a very strange situation. But velocity has a direction. It has both a size and a direction. And it turns out, speed is just, if we're talking about any instant of time, the speed at any instant of time is just the size of the velocity. So if I'm moving at 3 meters per second east, my speed is 3 meters per second. My velocity is 3 meters per second east. So it's just the magnitude of the velocity, the size of the velocity. And to express vectors, we draw them as arrows, because they have a size and a direction. So here are some examples. This is an arrow expressing 40 kilometers per hour. To draw an arrow expressing 80 kilometers per hour, we draw an arrow that's twice as long. These are both in the positive direction. So we're primarily deal with one-dimensional motion. And then in that case, speed is just the absolute value of velocity. Velocity will be positive or negative, that kind of thing. Here, this is negative 40 kilometers per hour. It's in the negative direction. So this way is plus, this way is minus. This is negative 80 kilometers per hour. You can see the negative 40 kilometers per hour is just the 40 kilometer per hour arrow pointing in the opposite direction. The negative of the velocity is just that velocity pointing in the same size in the opposite direction. So if we added these two velocities together, 40 and minus 40, they would cancel out. Same with 80 and minus 80. So vectors in one dimension can be both positive and negative. So we have negative velocity of the car plus velocity of the car. These cars are moving at the same speed, but in opposite directions. Here we have velocity of the man. And the vectors can be both positive and negative. And the plus direction is this way. I should try and get that background. What the heck was talking about? Now, if we want to talk about average speed, the average speed is the total distance traveled over the time it took to travel that distance. So average, V average. One problem is that speed and velocity are both written with a V. Is, total distance over total time. But average speed is total distance traveled over the time it took to travel the distance. The distance is the actual length of the path you traveled. The instantaneous speed is the speed of any object at some instant of time, i.e. the time period you're looking at is very small. And you get that by glancing at a speedometer. We're doing calculus. We're not going to be doing calculus. But that's what a speedometer does. It measures instantaneous. Velocity is similar, except there's a direction involved. And that means the average velocity is displacement over time. Now, displacement is the change in position from where you started to where you ended. It does depend on, it is path independent. It just depends on the starting and ending point. So this, is final position minus initial position over time. And the instantaneous velocity is similar to instantaneous speed, except it has a direction. The reason that average velocity doesn't depend on the path is because all the directions can cancel out in such a way. The only thing that ends up being important is where you ended up compared to where you started. So the displacement is if you have a vector that started where you started and ended where you ended, and you get a straight line connecting those 2 points. That's your displacement. It's your final position minus your initial position. So, for example, if something like the Indy 500, where cars go around in a circle on a racetrack for a very long period of time, their average speed is very high. Their average velocity, if they start and end at the same location, is 0. because their net displacement is 0. Because, a way to think about it is that if I start here and I walk over here, turn around and walk back, I have some average speed that was maybe a meter per second. But my velocity going that way was canceled out by my velocity going that way. When I take the average, I end up at 0 because I started and ended at the same location. So here's an explanation of the difference between displacement and distance. Displacement is a vector quantity between 2 points. It's starting point and ending point. Those are the only 2 things that matter for displacement. Well, distance depends on the actual path you take. So both of these paths, this one and this one, have the same displacement, but they have different distances. This path is, of course, longer than this path. So that would give you, different distances, same displacement. And the general way that you add vectors is you connect them head to tail. If you have a bunch of vectors to figure out the distance, you just add up the magnitudes of the vectors. So here we have a bunch of vectors. This is length 2, this is length 1, this is length 2, this is length 2. If we add those all up, the distance is 2 plus 1 plus 2 plus 2. That's 7 meters. But the displacement, we go from head to tail and form a triangle. And we can use the Pythagorean theorem to figure out the length of that third leg. This side of the triangle is 4 meters. This side is 3 meters. So the displacement here is going to be the square root of 4 meters squared plus 3 meters squared, which comes out to exactly 5 meters. And the direction is roughly southeast. And I think that's where I'm going to stop for today. We'll continue chapter 2 next week. So I'm going to stop sharing and